Hello everybody. In earlier classes we had seen random access memory which is also read write memory. So, the user can write as well as read information from that memory block. In today's class we shall look at read only memory. Okay. So, from the user point of view reading will be done multiple times, but writing is to be done by the developer by certain mechanism, or it will be writing will be done in the factory end. Okay. And these are the concepts that we will cover. We shall see the similarity between decoder or circuit, the paradigm that we had used before, and read only memory. Then we shall see read only memory using developed using diode or transistor switch. Okay. And then as I said, it has this similarity between similarity with decoder or circuit. Okay. And essentially it is a combinatorial circuit or this ROM. So, we can have several combinatorial circuit designed very easily using ROM. So, examples will be given for a square root circuit, but one can develop many other circuit following the same design philosophy. And at the end we shall discuss programmable ROM, its different varieties. Okay. So, read only memory, in this the binary information is stored in certain interconnection pattern. So, what is that interconnection pattern, that we shall see shortly, and this pattern is non-volatile. Okay. Unlike RAM, the kind of things that we had discussed before. So, even if the power is off, once it is written by the developer or the programmer in programmable ROM or standard ROM at the factory end. So, it will remain available for reading, because the pattern is ingrained in that memory block. Okay. And so, the basic block diagram of a ROM will be something like this. So, M address input. Okay. So, this will generate 2 to the power m locations, memory locations, right, and in each location if n bit information is stored. So, n data outputs can be generated by invoking a particular set of address bits. Okay. And there can be additional control input like enable, etc. Okay. So, but this is the basic block diagram, right. So, there is no write option that you can see over here. So, it is mostly reading option, because writing is done in a special manner. Of course, somebody is writing, otherwise how can you read it. Okay. But that is done separately. Okay. So, let us see the similarity with decoder or paradigm circuit. So, we consider a 3-bit address A220 and 3-bit data. Okay. So, this example, this circuit that we see over here, I have taken it from our earlier discussion with decoder circuit in the combinatorial circuit discussion. Okay. Somewhere in week 4 or so. Okay. So, you can see this circuit over there. Okay. But just to compare and see how it is similar, we have taken it again in this particular discussion, right. So, this 3 bits means 8 address locations. So, this is the decoder output. You can see the decoder output 000, 001, 010, right. So, there will be a 3 to 8 decoder as we see, as we have seen in a memory block, right. After that, the information that you want to store, for example, forget about these functions f1, f2, f3. Okay. So, you can consider this is D2, this is D1 and D0, and in each of this location you want to store some information, some binary information, right. So, here is an example, say that you are storing 110 here, 001, again 001, 001, 100, 010, 100 or 00, and you can take some other value as well. Is it fine, right? So, if you do that, okay, then what you can see, this is what you require, this is what you are looking for from your memory, right. And if you look at this particular circuit, which is generating this this is the decoder outputs A prime, B prime, C prime to ABC, all 8 these lines, and this is the OR outputs which is taking specific values, right, and these specific values are in this particular truth table. If you put it in the form of a truth table, so D2 becomes your F1, D1 becomes your F2, and D0 becomes your F3. This is the way we have name has been given. We can give it in a different manner also, okay, change the order, etc. So then, so D2, this is there for 1 is over here, 1 is over here, and 1 is over here, right. So you can write this as a summation of this, the min terms 0, 4, 6, 0, 4, 6 for D1, which corresponds to your F2. Okay. So 1 is there here 0 and 5. So this is these two min terms you can add using a OR gate, and F3 1, 2, 3, and this is the 7. So that is what you can see. And after that, what happens? If you are just say invoking 0, 0, 0, so 0, 0, 0 over here, right. So then this line will be high and rest of the lines will be 0, all of them will be 0, right. So this line high means, okay, this is OR gate. So this is having an input 1, 0, 0. So this output will be 1, this will be 1, and this is 0, because all these are 0, okay, from the because of the decoder. So this output will be 1, and here all these inputs are 0, because coming from here. So all the inputs to the OR gate will be, okay, 0 to 0, right. So this output will be 0. So you will be reading, if you put 0, 0, 0 at its output 1, 1, 0 as D2, D1 and D0. Okay. Similarly, for every other location you can see that is happening. So if it is 0, 0, 1, what will happen? So A prime, B prime, C, this particular will be output will be 1 and rest all 0, these are all 0. So what happens to this input? Okay, input of this OR gate. So this is 0, 0, 0, because of this, that these decoder outputs are 0 for these respective cases. Similarly, over this is 0, this is 0. Here this particular one is 1 and rest all are 0. Okay. So this is output will be giving you 0, 0, 1. Is it fine? Is it understood? Right. So you place the location address bit, okay, and at the output, okay, you will get the way we have configured it D1, D2, D1 and D0 by this arrangement. Is it fine? So ROM is essentially a combinatorial circuit, that is what we have noted. Now let us move forward. We look at another such thing where this is a 8 cross 4 ROM that we are interested in. Okay. So A220 is my address bits. So it is generating all 8 possible locations in the memory, right. So this is the decoder block over here, right. So the first one is A bar, B bar, C, then A bar, B bar, C. Yeah, so this is first one is A bar, B bar, C bar, second one is A bar, B bar, C, and this is the way that we have seen it before, right. Now in each of these locations, this is D3 to 0. So this is D3, D2, D1 and D0. Again forget about this Y3 etc., which we shall take up later, right. And what is the information that we want to store? So we can take something which, as I said, this is fixed by the developer or the factory, you are not changing it again and again. So what you want to fix, you have to tell it in advance, okay. So it has to be told to the IC manufacturer, which will who will prepare a specific mask, okay, a photographic template of the circuit, and which will be used in the production of the ROM, okay. So say you have said I want in the first location 011, 0111, second location 1000, third location 1011, this need to be stored, okay. This is the way the rest of the cases. Okay. So, this is what is over there. Now, one way to achieve this, okay, which is equivalent to decoder OR, that part I shall discuss later, is by using diode switch. Okay, by using diode switch. Okay. What does it do? So, you can see this is the decoder output and these are the 4 lines, right. They signify the D3, D2, D1 and D0, right. And wherever 1 is present, you connected diode, connected diode, connected diode, and wherever 0 is there, at that cross point no diode is connected. So, that means here is one wire, another wire is just going over it, there is no connection between them. So, there is no connection between these two. Okay. So, this column over here, this vertical line is not getting any input from A prime, B prime, C prime line. So, they are not connected with each other. Here it is connected, Y2, Y1, Y0 are connected. Is it all right? So, when 0, 0, 0 is placed, what will happen? 0, 0, 0 is placed over here. So, only this one will be high and rest all are 0, okay, because of the decoder action. And at that time, so this is, there is no connection over here. So, at the input of over this line, okay, only 0 is present, I mean no connection, no current is flowing through this, no IR drop. So, I3 will be 0 and here there is a high voltage 1 is present. So, some 0.7 voltage drop of this diode also, okay, and then the rest of the voltage drop is occurring across this. So, which will be considered as logic high. So, this Y2 will be considered as high, Y1 will be considered as high, Y0 will be considered as high, okay, right. So, your D3 will be 0 and D2, D1, D0 will be 1, 1, 1. Is it fine? So, that way continuing for each of these cases, wherever a 1 is present in the memory, for example, 1 0 0 0. So, here there is a in the cross point diode is there, right, and rest of the cases no diode is present. So, this is the way when you generate a pattern, right, by masking process, right, and come up with this ROM, right. This is the storage that you will see in the memory block, right, this 8x4 ROM block, right. Now, as we had noted, so this memory is also is a combinatorial circuit, right. So, now if we represent D3 as Y3, a function, a Boolean function getting generated, and D2 as Y2, D1 as Y1 and D0 as Y0, right. Then this Y3 is what? If you look at the whole of it, earlier we are looking at each individual location wise. Now, if you look at all the columns put together for this particular Y3, the way we had seen in our earlier decoder OR arrangement, where specifically a OR gate is put, here we are not putting any OR gate, just resistance is there, but it is giving a equivalent representation, and that is what? That is, you will find that this is 1, 2, 3, 5, 7. So, these are the mean terms that is getting summed up. So, Y3, D3 that is also a Boolean function generator in the place of D3, which is generating this function. Similarly, Y2 is generating this. If you look at 0, 0, 3, 4 and 7, Y1 0, 2, 4, 6, 7 and Y0 is 0, 2, 5, 6. Is it fine? So, here we do not see a OR gate as such specifically put, only diode and resistance, but this is also giving you a decoder OR equivalent relationship. Okay, fine. So, this we can utilize in generating various important combinatorial circuit block. Okay. So, here is an example of a square error circuit using ROM, because essentially it is a decoder OR architecture is there, right. Even if you use diode or resistance and all at the cross point, and then output taken across the resistance, right. So, here in this example, so this is a 3-bit squarer input is there, for which squaring is to be done, and 3-bit. So, these are the different possible values 0 to 7, these are the decimal equivalent, right, and corresponding output is 0, 1 is 1, 2 is 4, 3 is 9, 4 is 16, 5 is 25, 6 is 36 and 7 is 49, and you can write them in binary, right. So, 0 is all 0, 1 is 50 and then 1, 4 is 0 0 0 1 0 0, right, 9 is, this is 1 0 0 1, 16 is 1 all 0 over here, 25 is 16 8 24 and here is a 1, okay. 36, so 32 and 4, these two you can see, and 49 32 16 and this is 1, okay. So, this becomes a kind of lookup table, that if this is the input, corresponding output should be like this, right. So, if you just look at it and try to realize using a ROM, okay, then you may think of that I need a 8 cross 6 because there are 8 inputs and 6 outputs, 8 cross 6 ROM, okay. But if you look at it closely, then perhaps you can see that you can do with lesser sized ROM as well, okay. How? You can see that D1 is always 0, okay. D1 is always 0, you can permanently connect it to ground over here, and D0 you can see whenever A0 is 0, D0 is 0, A0 is 1, D0 is 1, just following A0. So, D0 can be directly connected to A0, and for rest of the cases, you can see that say D2 is minterms, okay. This is 2, right, and 6, right, these two put together in a SOP realization, that decoder or the minterm getting added by OR, okay. So, for D3 we can see this is D3 3 and 5, for D4 4 5 and 7, and 5 for D5 6 and 7. So, only these 4 are required. So, we can have a 8 cross 4 RAM instead of 8 cross 6, right, because these two are already realized by a simpler means, okay. So, we can connect it in this manner, and within this 8 cross 4, this is the way the pattern need to be ingrained. Then this particular block will be a square circuit for a 3-bit input, isn't it? So, similar thing you can extend for a more complex circuit, and for example, squaring of a BCD number, right. So, squaring of a BCD number, so BCD input is 0 to 9, right, and the output could be in this case 0 to what, 81, 9 is 81, 8 is 64, 7 is 49, okay. So, this is the way the number will be there, and here what is asked is that the output will be shown in the BCD format, unlike the previous. Our previous it was a binary format. So, this is the requirement. That also is possible. How? We shall see. So, this is BCD squarer. So, if you look at it, that the number is up to 81. So, 2-digit number. So, 1 digit will be fed from one particular fed through one IC 7447 to a display, and another digit lower significant the 1, this binary coded decimal, okay. So, that will be fed to the 7447 and the corresponding decimal number will be fed. Is it fine? Okay. So, this is the overall this thing, and then we will look at having a particular pattern ingrained in a ROM. So, here in this example we show that the connection at the cross point is made through transistor, a BJT instead of diode. That is also possible. It can be done through MOSFET also, right. So, wherever this is connected like this, you can understand that this what you can see, if in this particular case right. This is 5 volt. Okay. So, if this is on, please understand the difference between what we had seen before and this one. So, if this is on, this is high, then this transistor will be off. So, this will be put to saturation, very low voltage 0.1 or 0.2 volt. So, this voltage here will be low. So, whatever you are reading here will be low. Is it all right? Clear? So, voltage at the input of this, the transistor makes the output low, right, at the cross point. And if at the cross point no such thing is there, then this output will be, you can see over here, this output over here, there is no connection in this cross point. So, this 5 volt will be coming over here, okay. And depending on the load impedance also, some voltage, some current drawn, some current will be dropped across this particular resistance, but that will be sufficiently small for which the output will get recognized as logic high. So, presence of transistor, okay, will give you a low value when this particular row is accessed. So, decoder output becomes high, and absence of transistor will make it high. Presence of transistor low, absence of transistor is high. Is it fine? Is this part understood? How the circuit is working, how the current flow and the voltage level coming over here at the output, these are the outputs. Okay. Now, if you have understood that, then the first one, the BCD inputs is say 0, 0, 0, 0, right. So, this one will be, this is a 4 line BCD to 10 line decimal decoder. So, this one will be activated, right, 0, 0, 0, 0, okay. So, this for this particular 0, 0, 0, this is getting activated Y 0, right. So, at that time what we want at the output, right, 0, 0, both of them should 0 here and 0 here, right. So, this 4 bit should be 0, 0, 0, 0, this 4 bit should be 0, 0, 0, 0, okay. So, accordingly all the transistors need to be present, because absence of transistor will make a logic high, one value present here, clear. So, next one is 1, so it should be 0, 0, 0 over here and 0, 0, 1 over here. So, 0, 0, 0, 0 and here it should be 0, 0, 0, 1. So, here you can see that the transistor is absent, right. So, when this line is invoked, okay, 0, 0, 0, 1 is present. So, this is decoded. So, all of these particular cases, these transistors will be on, right, up to this. So, this will be, output will be low, that is 0.2 volt, 0.1 volt, this whatever the saturation voltage or so. Here it is no connection is there. So, 5 volt with whatever the, because of the load current, some drop over here, it will be logic high, okay. So, similarly 4, 9, we take up just say one example over here, say 25, okay, 5 has been put. So, in this line, so it should be, because it is presented through 7 segment display. So, 0, 0, 1, 0 should come here, 0, 0, 1, 0 and here 0, 1, 0, 1 should come here. So, what you can see that 0, 0, 1, 0. So, this point we do not have the transistor, here 1, 0, 1. So, this point and this point we do not have transistor. Is it fine? And then it is connected to, this line goes to this 7 port, port 7 and through that to 7 segment display decoder. So, this way many different kind of lookup table kind of this pattern can be generated and corresponding circuit can be obtained. Okay. So, so far what we have discussed is ROM, which is the pattern is ingrained, pattern is prepared in the factory itself. Okay. But if a developer wants to put his own pattern, he cannot send it to the factory or so, okay, for which we have what is called programmable ROM. Okay. So, in this at the cross point, the connections that you are seeing, say diode is there. So, after that there will be a fuse. Okay. So, wherever you want the connection not to be there, you send a high current by which the fuse is burnt, okay, and the connection is lost. So, to begin with, you have all the fuses present, like this is the original thing. all the fuses are present in the OR plane. Okay. And this is the decoder, this is the fixed AND array which is acting as a decoder, right. And then whenever you want to put something, you just do accordingly to burn the fuses. So, this is the burning in process. Okay. So, this is destructively high currents are sent through diodes. So, for example, in the first location, if you want to store 1001, so when this is 0 0 0, what you want to store in that corresponding location is 1001. So, this decoder output will be accessed. Okay. So, at that time, this point and this point, if you want to store, so these two cross points, the fuses will be burnt. Okay. And similarly, other points, depending on what you want to store, the corresponding points will be burnt. Okay. And then here you have got the resistance and connected to the ground, which effectively gives you a OR gate realization. Okay. Now, in PROM, once you ingrain the pattern, you cannot remove it. Okay. So, then comes what is called erasable PROM, a further advancement here, where the data is written, of course, through a EEPROM programmer. Okay. And so, here the data writing is done through something called a floating gate. Okay. So, the MOSFET based realization, this memory cell realization, in this there is this is a normal standard MOSFET, the gate side, but here there is an additional gate called floating gate that is put over here. Okay. And by a particular phenomena, when appropriate physics works out, okay, so that we will not go into the details of that, tunneling, etc. Okay, the specific phenomena that happens over there, from electrical or electronics circuit point of view, what we understand is that in this particular floating gate, electrical charge, when it is stored, the threshold voltage increases. Okay. And when it is not stored, so threshold voltage is the normal threshold voltage that you see for the gate to work. Okay. So, threshold voltage, when it is higher than normal, usually considered as logic 0, and otherwise it is considered as logic 1, right. So, this is what is used in erasable PROM. So, this floating gate, whatever charge is getting stored or not stored, that condition is altered, okay, when the erasing process is done, right. And in normal EEPROM, it is done through ultraviolet light impinging on this particular IC through a quartz window, okay, where all stored charges get released. Okay, it becomes all equal, and then after that, during programming, you send a appropriate programming pulse of a particular magnitude, okay, which will ensure storage of charge in specific location. So, that is the writing part of it. Okay. And in electrically erasable PROM, so that is normal EEPROM, where ultraviolet light is used for erasing purpose. In electrically erasable PROM, the data is erased by removing the charge using a electrical pulse of opposite polarity. Okay. Instead of UV ray, now electrical pulse of opposite polarity is used for erasing. Okay. And of course, this is very slow, and after that came flash memory, okay, where which is faster than EEPROM or E square PROM, often it is called E square PROM also. Okay, this electrically erasable PROM, okay, where the data writing happens in blocks, which is of the size of say 512 bytes, instead of what happens for normal E square PROM, which is 1 byte at a time. So, that makes it faster. Okay. So, here is just one memory cell kind of example. So, during programming, as I said, the pulse is sent of high magnitude, relatively higher magnitude, and the floating gate the charge is stored, okay, whenever we require it. And during the reading process, both of them get 5 volt, okay. And depending on this particular case, this Q2 will be off if charge is there in the floating gate, because the threshold voltage becomes much higher, okay. And if it is on, okay, then it will be the normal operation. So, this will be on, this will be also on, and this voltage will be accordingly. Is it fine? Okay. To end, just we look at one particular EEPROM IC which you might be using in the lab, okay, which is IC 2716. It is often used in the digital electronic circuit lab. So, this is the this is a, of course, you can see there is a quartz window over here. So, this is a UV ray, I mean this EEPROM can be erased by using UV ray, okay. And when you want to read it, first a valid address is put, after that chip enable, and then output enable are successively placed, and then the valid output is obtained. Access time can be up to 450 nanoseconds. So, in that sense it is a bit slower, okay. And erasing, of course, by ultraviolet ray, which is shorter than 4000 angstrom. Recommended is 2537 angstrom. After writing, a opaque label is put over here, okay, to prevent sunlight or room light coming in, because those light has components which is less than 4000 angstrom. So, by which these information that is stored there can get slowly erased, okay. And for writing, of course, there is no data write in input. So, these data outputs that are there, okay, there only the data is placed for writing the TTL level data, and these are the address that will be there. And at that time a programming pulse that is there of 25 volt is used, okay. This output enable is at high, okay, and data to be programmed is applied at the output pins in parallel over here, okay. And data and address level are all at TTL, and when address and data are stable, a 50 millisecond TTL pulse is placed to chip enable, okay, right. And by that process writing gets done, and after writing a verification is done whether the data written is what was intended, and if verification passes, then the device becomes ready for the use. Okay, this is the way the EEPROM writing or programming takes place. Okay. Quickly to conclude, ROM is a device where information is stored in the form of interconnection pattern which is non-volatile. Essentially, it is a combinatorial device following decoder or architecture, and we have diode or transistor based switches placed in the cross points in the OR plane. ROM is factory made, but programmable ROM can be programmed by a developer to inscribe a particular pattern. Erasable PROM uses floating gate concept, where charge is stored to increase the threshold voltage of the transistor for a specific switching operation. Okay. And in EEPROM, erasing is done by ultraviolet exposure, and electrically erasable PROM, electric pulse used for erasing purpose. Okay. Thank you.